Now, forward state space planning is actually like one of the oldest ways of planning, and it's one of the newest ways of planning. State-of-the-art planners today all take this approach of forward state space planning with a heuristic. But it's not the only game in town. There have been a number of other approaches, and they're worth knowing about. And so that's the topic of today. There are two other main approaches to planning that you should know about. One's called regression, and one's called partial order planning. So we're going to talk about those today. Regression is just common sense. So it's pretty straightforward. In fact, it is so common sense that the person I like to credit with coming up with it is Aristotle. Aristotle said, and this is true about politics today, really. Like, we don't deliberate about the ends of our actions. We all want a strong, prosperous America. We deliberate about the means of getting there, how we'll do it. So not what the goal is, but what actions we'll take to get there. A doctor does not deliberate whether he shall heal, an orator whether he shall persuade, or a statesman whether he shall produce law and order, nor does anyone else deliberate about his end. They assume the end and consider how and by what means it is attained. Right? Planning is really the fundamental human activity. Usually there's great agreement about goals. It's really, intellectual thought is about planning. What means the goals are to be attained, and if it seems easily and best produced hereby? Well, if it is achieved by one means only, they consider how it will be achieved by this and by what means this will be achieved. If there's only one way of getting what you want, one action that will produce it, you have to think, okay, what's the action that will let me do that action? Right? The only way of having $1 million is by cashing that $1 million check. So how do I get the $1 million check? Right? Oh, I have to win the lottery. Okay, how do I win the lottery? I have to buy a ticket. Right? So how it will be achieved by this and by what means this will be achieved till they come to the first cause, the buying of the ticket, which in the order of discovery is last. Right? The first thing you will do is the last action you consider because you're reasoning backwards from the goal. What is last in the order of analysis seems to be the first in the order of becoming. And if we come on an impossibility, we give up the search. For example, if we need money and this cannot be got, we backtrack, in other words. But if a thing appears possible, we try to do it. So here's Aristotle doing backtracking search backward from the goal as a planning algorithm. So that's called regression search, or retrograde analysis. You're going backwards from what you want. Everyone understand the algorithm roughly? We're going to go backwards for the goal. What are the preconditions? We're going to actually consider the goal as an action, basically, like the hallelujah action. And that action has preconditions, which are the goal conditions. And then we say, okay, how do we achieve those preconditions? Well, here's an action that will achieve it. Try that one. Let me draw a little picture, maybe. Do I have a picture on the next slide? I don't think I do. No, I don't. So let's have a picture. Fresh sheet of paper. So here's our goal. And there are various preconditions on the goal. I don't know, maybe P and Q. And maybe we have an action that achieves P. So, I don't know, there's do P, and it gets P for us. And then, well, okay, P might require some stuff. Maybe P requires T, and maybe there's a do T action that will achieve that. And maybe the precondition of do T is that R holds, but maybe R holds in the initial state. So now we have a plan. Do T and then do P, and you're good. We're going backwards from the goal. Now, this is incredibly commonsensical, and the example they give in the textbook is great, which is going shopping. Going shopping. You know how many SKUs a typical retail store has on their shelves? Guess, like order of magnitude. SKUs, stock control units. how many things they sell, different things, different kinds of things. Like, Advil 8-ounce size children's formula is like one type of thing they sell, and then Advil adult size maximum strength is another one, and then pineapple fresh is one. Pineapple in a can in juice is, by Dole is one. Pineapple in a can in syrup is another one. Pineapple in chunks. Have you ever looked at a supermarket to see how many different things they sell in a modern store? I mean, you could not run one of these stores without a computer. It would be impossible. They don't have thousands of items in a typical store. They have tens of thousands of different items in inventory in a typical store in modern America. I went to Moscow once, and the typical store that I visited had approximately 5 items in stock. And it was extremely disconcerting. You go into this store, and it's like, here are the boxes of X. Here are the boxes of Y. And it's like, that's what we have today. And it's just crazy, incredibly backward at that time. This was in the 80s.
That's like that story where, I forget who was the Russian president at the time. He was meeting with our president, and then they needed to pick something up, so they just stopped at a supermarket, and he thought it was like a hoax. He's just like, what? You just could walk into a supermarket and buy something?
Yes, it's amazing what we take for granted. Anyway, so let's imagine we're doing forward state space planning, and I need bananas and milk, right? Okay, so I walk into the store. I'm going to execute the buy action, right? How many applicable actions are there in the forward direction, right? If there are 50,000 items, then my branching factor is 50,000 for the buy action, right? So first I instantiate 50,000 children. One of them is buying bananas. The other one is buying milk. They'll both get good heuristic values and go to the front of the queue. I'll expand one of them. I'll now branch 50,000 more ways, maybe 50,001, because now I can go check out. So now I buy my other item. So I've instantiated 100,000 nodes to generate the plan, like buy milk, buy bananas, right? Which is ludicrous. Like, don't tell me when I go to the store, I am thinking of buying every possible thing and I just happen to choose the ones that are on my list. Like, no, I work backwards from what I need. Like, oh, I need milk. I'll go to the milk section and pick the milk and put it in my cart and purchase it. Right? It's incredibly intuitive. I think it's a miracle that forward planning could work at all. I mean, it's nuts, basically, when you think about it. Like, I'm going to imagine going everywhere in this room, and one of the places will be to the door. So if I'm trying to get to my office, then the action that takes me to the door will be weighted more highly, and I'll select that. And now you're going to tell me I have all those other nodes sitting on my open list, clogging it up somewhere? I mean, it's just crazy. So a lot of the forward planners that are successful today have all kinds of special tricks for recognizing actions that are obviously stupid and throwing them out. Regression planning has none of this, right? It's like, I need milk and eggs, so I better have, in order to have the milk, I better do the buy milk action. In order to have the eggs, I better buy, or bananas, I better buy bananas. And so there you go, like no branching, it's just like very obvious what to instantiate, and now you have a plan. So why is regression, so did everyone understand regression planning? It's basically just like forward state space planning, except instead of starting off with the root being the initial state, the root is the goal state. And you look at you look at the preconditions of the goal and try and fill them, and you work backwards. Now, let's see. Let's take this one step. Let's see. Okay, there's something not quite right about what I said, though. So, if there's a complication here, which is that in the goal state, we don't actually have a goal state for doing strips planning. The goal is asymmetric with the initial state. The initial state is fully specified, The goal state, we just know that have some things that we know to be true. So it's not actually a fully specified state. So if we're wondering, for example, what actions are legal to execute to get into the goal, we don't fully know. It's a little dicey. So the state space for a regression search is actually different from the state space for a forward search. Since the goal is a partially specified state, you can actually look at it as representing a set of states. So if my goal is to be, I don't know, rich and famous, or no, I don't really care that much about fame. Rich and healthy and out of jail, and still married to my wife. So, there's a whole set of states described by that. Like, there's one in which my house is pink, one in which my house is brown, one in which my house is white, one in which my house is purple. So you can think of these partially specified states as being state sets. So when you do regression search, you're actually searching over sets of states. And the initial state, the initial root of the tree, the initial node, the root of the tree, is the set of states in which the goal is true. And search is actually a little complicated. The applicable actions are the ones where, actually this is fairly straightforward. The applicable actions are the one where the positive effects, at least one of the effects is present, where the deletes are not present. So if the action deletes some stuff, you want it not to be in this set of states. Notice that there can be positive effects, add effects, that are not present here. Right? It could be that this action makes my house pink in addition to giving me $1 million. And that's fine, as long as it's consistent with this set. Right? So and that means that the deletes are not present there. And non-deleted preconditions are present. So if the paint my house pink and give me $1 million action requires that I had pickles for breakfast, then the fact that there's a half-empty pickle jar in my fridge has to be true here.
If you can have effects that aren't currently in your state, couldn't you just start out with a goal state that has everything you need, and then kind of add to it as not start out with a set, essentially? Because you don't, it could take a lot to enumerate all the possible goal states, right?
Yeah. We're representing the set just by listing the things that are true of every member of it.
Oh, okay. All right.
Yeah.
All right.
Yeah, so this partial specification of the goal is standing for a whole set of states.
Okay.
Exactly. Yeah. It's a very concise way of representing the set. This isn't actually, this line here about non-deleted preconditions being present is not strictly true, now that I think about it. In the children, you'll have to add all the preconditions, but you don't actually have to have the non-deleted preconditions present in the parent state, because those could, as long as we're not inconsistent with the parent, we're okay. Does everyone understand why? So like that pickle jar, for example, if the goal state doesn't say what the state of my fridge is, then if the precondition is that I've got a full jar of pickles, then that's totally fine. We'll just make sure in the child to say, by the way, I've got a jar of pickles in my fridge now. Because that's one of the preconditions of the action that we just regressed through.
When you say child, do you mean which direction?
Okay, here is rich and happy. Right, so here is the cash check action. And in this state, I have a check So having a check is a precondition of cash check. So this is the child state, and it represents the time just before I cash the check. So it's later in the order of discovery, but first in the order of becoming. Is everyone following? So regression planning, it is a little tricky because we're not planning in the same order that the actions are happening in. So now this is also a state set, right? This is the set of states in which I have a check. Like I could have a pink house or a red house, it really doesn't matter. Now maybe if there's only one way of getting the check, which is to win the best polka dotted pink house contest, like that might be one way of getting a check. So this is the pink house contest. Here is a state where I've got a pink house. Now there might be another way of getting a check, which is like inventing a robot. Boy, this is not a good idea to draw pictures. So here is the state where I've got lots of robot parts lying around. And these represent different plans, right? Here's the plan where I build the robot and cash the check. Here's the plan where I enter I win the contest and then I cash the check. Here we'd have to instantiate an action to actually paint the house with a paintbrush. So this is regression. This is regression search. You can see why I'm not an art major. So did I answer your question?
Yeah.
Okay, great. So the successors in the search space are the predecessors in the plan.
Which of those plans would regression choose?
Depends what planning algorithm you use. I hope you're trying to do something like minimize cost. The building of the robot probably doesn't cost that much, depending on how you value your own time, but buying the parts is expensive. A Velodyne LiDAR costs like $75,000. Now it can see out to 500 meters and does a full sweep of the entire environment 30 times a second and has angular resolution of 2 degrees, but so it's very expensive. So that action is going to put a big hit on your G cost. The painting your house, to me, seems like the cheapest plan. So I'm guessing it'll choose that one.
Because you own the house.
That's true. I already have the house. Yeah. That's true. Yeah, it could be overall. Maybe the robot's cheaper.
For me?
A Velodyne laser is cheaper than a house. Yeah. Other questions? So it's just a state space, right? You can search it however you want. I suggest A star, personally. Okay. Matt, can you make a note that this slide needs revision, please? So the children, we remove the ads, we add the preconditions, and the goal of the search is that the state set is a subset of the initial state. Right? All the things you require to be true are true in the initial state. Because in all of these regressed plans, the set of states you're talking about is really, those are the preconditions of doing the plan that ends at that node. So right here we need to have a check. Here we needed to have a check. Here we need a bunch of robot parts. If in the initial state we have a bunch of robot parts and a peanut butter sandwich, then this state is consistent with the initial state. This state set is consistent with the initial state. Because we don't care about the peanut butter sandwich, but God, we really need the robot parts. Because then we can execute this plan.
And the peanut butter sandwich can lead to being happy. So.
There you go. Absolutely. Absolutely. I got mixed feelings about peanut butter sandwiches, I have to admit. If you heat them a little bit, I like them better. It can get real creamy. Yeah, so it's got to be, yeah, peanut butter and toast. I'm getting hungry. This is not good. I haven't had a peanut butter sandwich in a long time. Honey? Honey. That sounds too sweet. We had an algorithm called PB&F, actually, that we developed. Yeah, we had to put a little footnote in the paper because it was for an international conference and the reviewers didn't quite understand what it was about. Apparently fluffernutters are a New England thing. I didn't even realize that. Like, they don't even have them in the South. Yeah. Talk about poverty. Yeah. Yeah. Poverty of the spirit. Okay. So the initial node is the set of states in which the goal is true. You regress back through the actions. At all times, the node represents the set of states that is consistent with the plan you're constructing, and you've reached a goal when your state set is consistent with the initial state. So the goal here is not the goal of the planning problem, it's a goal node for the search. Right? Don't get that confused.
Initial state and initial node are different, correct?
Yeah. This is just a terminology nightmare. That's why I say node, as opposed to set of states. This is not state space search. I want to point out, this is set of state space search. Or maybe we call it states space search. It's not a state space search, though, okay? Everyone understand the difference? We're going backwards through sets of states, not forwards through states. Okay, good. So it's a regression. It's a totally intuitive idea. To write it down formally is actually a little bit non-trivial. Doesn't assume reversible actions. A lot of people think, oh, well, you can't do regression planning unless you have actions in both directions. Like I can either cash a check or go to the bank and money appears in my account and they give me a check. But that's not true. Right? In regression, you're inverting the actions yourself when you regress through them. Okay? We're not running an action forwards. We're running the action backwards by removing the things that were added and adding the preconditions. So you can do regression search even in a domain where actions are not invertible. Like falling off a cliff, for example, a classic non-invertible action. If you're doing robot planning and the robot falls off a cliff, usually you can't undo that unless you have a very, very fancy robot with a jetpack. Like that the Arnold Schwarzenegger movie where there's like the pile of silver liquid and it turns back into the robot. That is so cool. So if you have one of those robots, then okay, maybe everything is invertible. But for normal robots, like once you go, there's no action that takes you from a pile of rubble at the bottom of the cliff to a nice robot going fast at the top. So you can still regress through there. Like if the goal is to have the pile of rubble, you regress through the jump off the cliff action, and now you're at the top of the cliff. Even though there's no action that goes in that direction. This is kind of bogus with the lower branching factor. So I was giving the intuitive example before of going to a supermarket, and I was saying, well, God, it's very intuitive that I would just want to buy the milk and buy the bananas. But have we really achieved that? Have we really achieved that here with this formalization of planning?
Guess there's other ways to obtain milk.
No, it's not even that. It's that. I mean, the point was to cut down on the branching factor. But yeah. I mean, I guess that's not only are there multiple ways of achieving milk and bananas, but there might be a zillion things I can do that are consistent with the goal state because it's underspecified. We've tried to cut them down by only allowing you to do an action that actually does contribute an effect to the goal. But there might be a zillion of them, and they might not all be directly contributing. So we don't quite have the perfect intuitive planning algorithm yet. We can still we still have this branching factor problem. And furthermore, and this is the real killer, we're actually searching a larger state space than we were before. Because before we were searching, when we were doing forward planning, if you think about all the possible states you could ever visit or nodes you could generate in the search, you could generate all possible states, which is where every literal is either true or false. Right? So if you have n literals, there are 2 to the n states in a forward state space search. In regression, it's worse because you're dealing with sets of states. So a literal can either be true or false or not mentioned. So the state space is actually 3 to the n for n literals. Furthermore, the big downer, I didn't even write on the slide. I don't know why. Is it on the next slide? Yes, it is. Furthermore, it's actually a lot harder to generate a heuristic here. You're trying to see, given a set of states, how expensive is it going to be to get there from the goal, from the initial state? And that's a hard problem. Yeah, there are. I don't know any technique for doing that other than doing. Some people have proposed doing planning graphs forward from the initial state to get to the regressed state, and that does work. That does work. Why does nobody do it? Oh, good question. Why does nobody do that? It actually has one very good advantage, which is if I'm doing regression, maybe I'll just draw it this way. If I'm doing regression back that way, and at every set of states here, I'm computing a heuristic from the initial state, and I compute a planning graph forward until I make all these literals true. The planning graph depends only on the initial state. So as I do more search in the reverse direction, I can reuse that same planning graph. I don't have to recompute it. One thing that was mentioned last time with using a planning graph for forward state space search is because the initial state is different for every node. The current state is different for every node. We have to recompute the planning graph entirely new every time. Okay, so why do I hate regression search so much if, in fact, you only have to compute the planning graph once? Oh, that's a good question. For some reason it doesn't work. I can't remember why. Why is the planning graph not useful in this direction? You've got a set of goal literals. We don't really win on the branching factor. The state space size is larger. Computing the planning graph only once would seem like a big win. Why is it not? That's embarrassing. Do I have it on the next slide? Let's see. So in progression, we have known states, strong heuristic. Expressivity. Well, that's a big one. Branching factor, irrelevant states, relevant states, larger space, weaker heuristic. Yeah, why do I think the heuristic is weaker? Yeah, I'm going to have to get back to you on that. I don't remember why. Let me talk for a second about expressivity, though. Let's say I'm a poor, unfortunate graduate student, and I had to do the graduate version of assignment 1. Does anyone remember what that was? Batteries, yeah, batteries. So the point is you do some actions and vacuuming and stuff, and that uses up battery power, and you're going to have to stop at the charger and recharge. In the initial state, I know what my current battery level is. In the goal, unspecified. Greater than 0, sure, but unspecified. So if I'm doing regression, going back, when do I insert a charge action? I don't know. When I've used enough battery power in the reverse direction that I know I'll need a charge to get to the goal? Well, maybe, but we still don't know if you need that in order to, we don't know, that might not actually be the cheapest place to do it, depending on what your charge was in the initial state. So it's very tricky to deal with these things called resources in regression planning because you don't know their states at the end of the problem. So if you want a very expressive planner with all kinds of fancy stuff going on, forward state space search is really easy because all you have to do is be able to forward simulate your system. But going backwards is usually much more difficult. Partly because the goal is unspecified, and also for some systems it's just a much harder problem to solve. For example, if you're doing robot control, for example, finding what state you needed to be in order to get to a certain state is harder than just forward simulating what happens if you turn the wheel right for most systems. So anyway, so this is usually much more flexible to go forward than to go backward. So for all these reasons, backward search is actually not used much anymore. There was a planner in like 96 that was pretty successful that did this planning graph trick. But that's like the last regression planner that I know of that was really state of the art. Was there a question over here somewhere? No. Okay.